name is Richard Correa. This is Data Recovery Tools, March 14, 2019. Today I'm going to cover a subject that's kind of complicated, but it helps you decide if a file that you're trying to undelete, a file that's been deleted and still has the full file name, hasn't been to the recycle bin, which I'm going to cover in another video. But if this file has been deleted, has a full file name, if there's a chance that it can be recovered without having any corruption. So the way NTFS works is, actually the way all file systems work, is that they have an area of the disk, a record that they keep for each file that's on the disk. In the case of NTFS, it's stored in the master file table. And each file has a master file table record. It's 1K long. And in it stores all the information. The date it was created, the last time it was accessed, if it was deleted, the size of the file, and a million and one other things. There's all kinds of stuff in there. The most important thing it keeps, I shouldn't say the most important, but one of the more important things that it keeps in there is what's called a run list, or in layman's terms it would be a cluster map. And what it is, it's a map of on the disk where the data for this particular file is stored. So if you have a file, if you have a cluster size, this is a map of the clusters. So the standard cluster size for NTFS is 4K, which is 8 sectors usually, unless you have a 4K drive, a sector that has 4K sectors, physical sectors on the drive. Then it would be 1 sector per cluster. But the size of a cluster for NTFS is 4K, 4096 bytes. So if you have a file that is, let's say, 8,000 bytes, then you're going to take up a full cluster of 4K and then a partial cluster of another one. So you're going to have 2 clusters to store a file that is 8,000 bytes. If you have a file that's 10,000 bytes, it's going to take 4 clusters to do that, or 3 clusters to do that, rather. So, and that's how it works. This is stored, Microsoft stores this in the most convoluted way. They use what's called a run list. And I'm not going to go into how they store it. All I know is that when I had to write the code to parse that, it was really painful. And there was a lot of code out there, and I had to kind of piece everything together. But it was brutal. And then trying to do it for a piece of software that's going to recover data. The assumption is from Microsoft, when they go to load a file and then they go to read it in, is that the run list is intact. But if you're trying to recover data from a broken file system, you can't make any assumptions whatsoever. You can't assume that the records are going to be okay, that the run list is going to be intact, that something didn't get smacked, whacked, woke, whatever. So you have to put in all these extra tests to make sure that when it goes to load the run list, that it does in fact load it correctly, and that it doesn't smoke your piece of software and drop it to desktop, which I'm sure you've all seen. So I wrote this piece of software here. This piece of software here, DRT File Undelete. This was the last time I updated. It was on March 4th. This software has a diagnostic that I put in it to illustrate how to watch for cross-linked files. So now we know that a file has a record in the master file table. This record in the master file table holds all pertinent information about the file, including where the file is stored, by using a run list that will generate a cluster map. In addition to that, Microsoft uses what's called a bitmap record. It's pretty much self-explanatory. For every cluster that resides on a volume, so you may have millions of clusters on a volume. If you have a 1 terabyte partition, a 2 terabyte partition, or volume, or whatever, you're going to have how many 4K blocks or clusters can you have within a 1 terabyte partition or 1 terabyte drive? Millions. So Microsoft uses this bitmap record which is also stored in the master file table, by the way. It uses this bitmap record to keep track of every cluster that's been used and every cluster that is available for use. In other words, they put a 1 in a bit, not a byte, in a bit, if the cluster is being used. They leave a 0, it's off and on. They leave a 0 on the bit if the cluster is not being used and is available for use. And Microsoft uses this for a multitude of things, but mostly to keep files. When they go to store a file for the first time, they will use this bitmap and they will find a space that will store the file contiguously, which means no fragmentation. They don't like doing that because there's a lot of overhead, especially with the run list. And the more fragmentation, the harder it is on the drive, the harder it is on the operating system, and the harder it is on speed when it comes to loading the file system. So you have this bitmap that has this map of every cluster, and every file registers its bitmap, its run list map, or this cluster map with the bitmap. So you have a file that says I'm taking 4 clusters from cluster 100 to 103, and the bitmap will reflect that. It'll say, okay, I am marking off this space from cluster 100 to 103 that you have allocated that, and that is now being used, and that puts a little 1 for every bit. The mechanics of the bitmap are such that they are broken up into 64-bit int64s, variable type or value type or data type rather. So you have a 64-bit or 64-bit number that stores a 64 clusters, the status of 64 clusters. So one 64-bit number will store the status of 64 clusters. And that's how it works. And then you have this long bitmap, and it's the best way to do it actually. It's really very simple, and it works, and it's very fast. But it's mostly used, like I said before, to make so if Microsoft has to save, knowing that it's going to save a 100 megabyte file, it goes to this bitmap in the master file table and says, okay, I need to find an area that will store a 1 megabyte file without fragmenting it in one contiguous shot, because that's the best way to store things. It's really easy. The run list, everything is nice. Everything is wonderful if you can do things that way. The way files get fragmented is they are saved over and over and over again. So you may have a file that you've saved on a disk, and it's saved it in this nice little 1 megabyte area, and it's all contiguous. It's one run. It's all there, no overhead. But then you read it in, let's say it's this 1 megabyte spreadsheet. And then so you read it in, you edit it, and you save it out. And then listen, it may go back and it gets bigger. So now it's not 1 megabyte, it's 1.1 megabyte. Well, you may have a little space still in there, but sooner or later what's going to happen, you can't save the file in a contiguous run in one shot. Sooner or later, you're going to have to find another space because you've edited the file. That's why, to a large degree, unless you're editing it, pictures are usually easy to recover, even though you've lost the file names and everything else, because they are stored contiguously. When you first dump a picture from your camera, let's say, or from your phone onto a hard drive, then the fact that you're only saving it and you're not editing it or changing it or making it larger, and that file is going to be normally 9 times out of 10, actually 99 times out of 100, it's going to remain contiguous because you haven't edited. It's the act of editing a file that causes the problem. So what we're going to do here is we're going to take a look at a file that I have on my disk that I saved. It's this file right here. Let me bring it over from my other monitor. Here we go. It's this file right here, and that's the size of the file. It's just a BMP file, okay? But this is still in the active file system, okay? So we're gonna have a 300, almost 350K file in the active file system called this. Now, I've rigged this software now to not look for just deleted files. It looks for anything. It actually looks for this specific file now so I can do this demonstration. So I've adjusted my source code, which is there. That's the source code for the software. And this is actually the source code that reads the bitmap here. And this is some diagnostics in here so I can illustrate exactly what's going on. So there's the diagnostic screen. There's the actual software. And then there's this. I'll be able to illustrate exactly through this calculator to show the binary of how these bits work. So first thing we want to do is we want to, with the software, I want to mount all volumes that I have on my drive, on my system. So, and you just got to wait because sometimes they're asleep or whatever. But if you follow this down, these little prompts down here, it'll tell you. And then finally, when it's finished, it'll tell you volume scan complete and found 5 recognized volumes. Now I've stored this on this volume here. This is just an NTFS. This is just a volume that I made for the demonstration purposes. And so what I'm going to do is I'm going to double click on that, and it's going to go out and find all the files. It's going to go out and find this file, the same device, this one right here, same device warning BMP, which is for another piece of software. But so I double click on that. Sure enough, it finds it. And in doing so, it also shows you the bitmap for the storage, for the actual bitmap. This isn't the run list, although I derive it from the run list. This is actually the bitmap. So this represents a group of files, a group of clusters here. This represents the first cluster. So what I do is I say, okay, I pull this data from the bitmap record in the master file table to see if it is occupied, and it should be. It should be occupied. If I put this number in here, FF, 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 what is it, 1, 2, 3, 4, okay, FF, FC, or no, it's C0. FF, 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 yep, C0, C. So let's take a look at this. See these here down here? Each one of these ones says this cluster is occupied by the file, by this file here that we're actually working on. So, and this is only on a 64-bit block basis. So here you have cluster here, here. So now you have, if you multiply this, 1, 2, 3, 4, 5, 6 times 4 is 24 plus 2 is 26. So we are represented here 26 clusters up to let me see, up to this point right here. See this right here? This is the last cluster, actually not 24, 26. So you can see here 0 to 25, we're still using the same block, the same value for the block, and we're still using the same mask, or the mask is still part of that cluster. So what we're going to take a look at now is this is the first cluster. So this is the first cluster within the run map and then we're comparing it to the bitmap. So here is the value of 4, which would be here. If we take a look at binary, we can say this is 0, this is 1, 2, 4, 8. It's all the same. 1, 2, 4, 8, 1, 2, 4, 8. It's all the same. So in binary, this is 1, 2, 4, 8, and then you combine these. That's how binary works. You combine these to create larger numbers. So if you were to show all of these, and you add these two together, so there's nothing in 1s, there's nothing in 2s, but we do have value in 4, and we do have value in 8. 4 and 8 is 12, represented in hex. That is C. That's what this is. That's what that is. So this is 12, and then this is 15, which is F represented in hex. C is 12 represented in hex. F is 15 represented in hex. So, and now we want to do is we want to see, so this is 4, and it looks like it's on because there's a 1 there, right? So we are masking this 4 here, and we're taking and we're comparing it. It's actually called ANDing it. We are ANDing it with this to see if there's data there. And sure enough, there is, because we see it here as a 4, and we see it here as a 4. And so what we do is we go through this whole bitmap. We go through this whole mapping sequence, and we find that, yes, indeed, all the way up to the end. See how this is set to 2 here? So now this was 1 here, 2 here, that's 3. That's the last one, and it stopped. So we know that all of the bitmap shows that this file's cluster map within the bitmap is active. It's being used. And it should be, because the file is still in the active file system. But this is what we're going to do. This is the illustration here. This is the whole ball of wax right here. We're going to delete this. I'm going to use Shift Delete to just whack it. And it's also so because it'll keep the same file name. So we're going to click on that, Shift Delete. It'll ask me, are you sure you want to permanently delete this file, blah, 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 and the answer is yes. Okay, so now this is gone. It is no longer in the active file system. So, theoretically, when I go to scan this again, this shouldn't be FFFF, this should be all zeros. Everything should be zeros. Now the mask will still be the same, but these will be all zeros. This will be the same thing. This should be the size should be the same. The resident should tell me that there's non-resident data in a single run. It should also tell me the name of the file. The only thing is, it's going to tell me that this file is deleted. And the way I know it's deleted, that these should all be zeros. So let's run this again and see what's the what. So we're going to go down here. I want to scroll all the way down. I want to make sure I don't miss this. Okay, so let's click on this. Okay. And let's see what's happened here. Now, lo and behold, everything is exactly the same, and this is the deleted file. But see how these are zeros now? That means that these clusters within the bitmap and the master file table are now available for use. They're all zeros now. They're not marked. Everything is 0 all the way down. So this file, right now, if we were to try and recover it, we would be able to do so this is the way it was when it was active. See how it's all has all the data in there? This is active now. See how it's all being used? This is the active file. Now as we go down here, actually this is after we've deleted it. And now these have all turned to 0. It's actually pretty fast, to tell you the truth. It's actually kind of a marvel of Microsoft science. Go figure. So now these are all zeros. Now, think about this. This was a 350K file, right? That's how big the file was. So now this is space that's now available for storage. And you have this picture, and you want to recover this picture. But before you do, you save something else on top of it. You save something else onto the drive. So what I'm going to do is I'm just going to grab something here. See if this actually, this part here I'm not quite sure if it's going to work properly or not. But let me see if we can find a file on here. Fairly large file. That was not a good idea. There's the source code there. Let me see if I can find a file. And then what we're going to do is I'm going to take that file and I'm going to copy it over the top of, I'm going to copy it back onto that file system. Hold on a second. I'm just trying to find a file to do this. So I probably should have done this before I actually did this little experiment here. Okay, so here we go. Okay, use that. about, there's got to be something big enough on here to kill. Let's kill this thing. All right, let's try this. I don't know what this is. So it's some kind of change log. So copy it, and I'm going to. So I've copied it from there, and I'm going to copy to the L drive, which is where we had this. So copy, paste this to there. Okay, now, theoretically, what should have happened here is that that space that we were looking at before was open. Let's go back into this here. Where's the calculator? There it is. Okay, so this space is open because it's all zeros now, right? And if we were to recover, since there's nothing else in there, we should be able to recover, no problem. Now let's take a look and see what happens when we see if the space is still available. Well, it killed the run list. There's no file anymore. It killed the file. So not only is the file not there anymore, but the run list is not there anymore. So even if you wanted to try and recover this file, so what happened is, not only, so it changed, and I'm entering the master file table. The way Microsoft deletes something is that it'll mark it. It doesn't delete the error record of the master file table. All it does is marks it as deleted, and then frees up the bitmap. The next file you save usually takes up the next space in the master file table. So what happened was, is that this saved it over the top of that record. So it whacked everything because I'm not getting that. But let's see if we can find, let's change the software now. Actually, we can take this here. We can actually find out something here very quickly. Okay, so the cluster was 7910. That was the cluster where this was stored, and it stored it for 88 clusters. So 7910 stored it for 88 clusters. Now, we're going to get out of the software. Let's name this thing changelog. Okay, now I'm going to go into the source code. And I'm going to find where I'm actually scanning the volume and where I've actually hard-coded the scan, which is right there. So I'm going to change the name to changelog. Actually just change, there's nothing else on here. C-H-A-N-G-E, so 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so 6 bytes. So we're going to save this, recompile it. So if we find a file that has the word change in it, we're going to display all that stuff we had on there before. So let's go back to the bitmap handler. It should be there. Let's go back to calculator and let's bring up the software. Put the software there. There's the calculator. Let's bring this down here. Okay, so once again, let's mount all the volumes. You'll see it starting to there. They're all there. Now this changelog is on this drive here. Let's double click it. Click OK. And let's see if in fact it stored it in basically the same place. 7822 cluster. The other one was 7910. So theoretically it did. It actually overlapped it. Yeah. So even if it would have kept the file name and everything else, it would have stored this file right over the top of it. Wow, there's something else stored there too. See this here? This would normally be zeros, but it's not. There's something else being stored here as well. Let's find out what it is. Let's see. Let's delete this file. Shift delete. Yes. See if there is actually. So this part here, from here on over, should be zeros, but we should still have stuff in there. So let's slide down here. And let's see if that's true. Let's see if I can actually, if that actually happens. Sure enough, this is another file right here. This is the file that we were using, and this is actually another file that bled on that has another bunch of clusters there. Interesting. So, anyway, so now you understand how cross-linking works. If I was to save another file onto there, if it didn't whack the file name, it would show data within the clusters instead of all zeros, which is what we have here. This is a perfect scenario here, all zeros. And now within this piece of software here, which I've written and I'm going to release fairly quickly, next couple of days or so, I have, see this right here? This says link. It's going to tell you if you have a bad link, if there's actually something that's been overwritten into there, and the chances of you actually recovering your data. So that'll be in there. And then I think I want to put in here a diagnostic that you guys allow you guys to dump it, so you can actually take a look at it and see if in fact do your own diagnostic to see what's going on. So anyway, that's it for this video. I hope you enjoyed it. The next video is going to be something about actually how to use this software to undelete a file that has gone through the recycle bin. See, we just clicked and deleted. We clicked on it, we had shift deleted, and so that doesn't go to the recycle bin, and it keeps the file name intact, which is easy enough to recover. But when you go to the recycle bin, Microsoft does something magical to it, and so we need to talk about that. So that'll be my next video. Thanks for watching, and let me see if I can get my stream going up here. Yeah. So we're good. Thank you very much. Take care, and bye-bye.